like I said, the Antikythera, which I'm just murdering, mechanism. If you want to see more, they have one on Nova. It's very, very well done. You can find it on YouTube. But this mechanism was found 100 years ago on a shipwreck off an island of that same name. The ship sank during the times of the ancient Greeks. A blob of rock was found among the debris. Wow, I can't talk. The debris. Using X-ray technologies, discovered it was a mechanical device. It was a calendar, celestial guide, and listed the Olympic event schedule. So literally the schedule. So imagine you going to the store today and you wanted a watch that was a calendar, told you when there was a full moon, and would tell you when the upcoming Super Bowl was or when the upcoming Olympic events are. This was doing this around the time of Christ. That's amazing. And it's made up of all simple machines, which is very cool. All right? Any questions about this device? All right? Let's talk about, we need to talk about some definitions. We're going to talk about simple machines. But first definition we're going to talk about, push definition. A force is a push or pull. All right? A force is a push or pull. Do a pull-up. That's a pull-up. That's a pull. Pull on a door open. That's a pull. Push-up. Doing a push-up. You're pushing yourself off the ground. Then we're going to, in physics, they have this really strange notion of work. We use, in physics, unfortunately, we use same words. When people think of work, they think they're getting paid and you're working at McDonald's, right, or something. But in physics, work is equal to force times distance times cosine theta. Don't worry about cosine theta for right now since you're in middle school. Don't worry about it. All you got to do is remember it as work equals force times distance. Work equals force times distance. We just said force is a push or pull. We know distances. All right? So we can start to calculate things. So for example, in this case, we say there's a 2 millimeter, he's here with the barbell. When he lifts that barbell up, he's gone a distance of 2 meters, a mass of 25 kilograms. How much work has he done? Go ahead and give me a question on that. Go ahead and write the answer down and answer to me as a question. How much work has he done? If he lifts 25 kilograms, 2 meters, how much work has he done? Answer it in a question, folks. Think about the formula we just had there. Work equals force times distance. Let's just say 25 kilograms is a force right there, times the distance. How much work has he done? Nice. Most everybody's gotten it. All right? Excellent. Yep. So the distance is 2 meters. The force here is 25 kilograms. Because we're looking at it that way. So we're looking at 2 times 25 kilograms, 50 newtons of force. All right? Well, it's not. It's all right. Now, let's not even worry about this. It's more of a direction of displacement. We're not going to worry about this. Don't confuse effort with work. Pulling on a locked door is a lot of effort. You're pulling on that locked door. However, by the definition of physics, no work because the door didn't move any distance. So work is not the same thing as effort. All right. Why did they develop simple machines? We've known they've been around since the times of the Greeks, the Romans, the Chinese, ancient India, all over human beings were developing simple machines. They do a couple things really well. Transferring a force from one place to another. You know, you start in the water and you're able to move grindstones so you can grind up wheat. You're taking that force from out of the water basically and using it to grind stones. Changing direction of force. Think of your car. The engine has a transmission that goes straight back, but your wheels are 90 degrees of that. Your wheels are right or left of you. And so you've got to be able to change the direction of force. The next one is increasing the magnitude of force, and that's another fancy way of saying how much force there is. Increasing that, or increasing the distance or speed of force. Okay? We're going to get, well, these are going to make a little more sense in a minute. Magnitude is a measurement of how much. And I'll put out a PDF, and we're recording this webinar so we can post this later. So we have 6 classes of simple machines. We've got the inclined plane, a wedge, a screw, a lever, wheel and axle, and a pulley. All right? Let's go through. Inclined plane. Those steps going up the side of that building is an inclined plane. Series of them. Inclined plane right here, 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 and here. Now, you can imagine if you just ran a ladder straight down, that would be the fastest way up there. It'd be also a lot more work. By increasing this distance, let me just restate just something there. It's a lot more effort, not work. Be the same amount of work. This distance right here, whether you go this way up these steps or take a ladder straight up, is the same amount of work. What is different is the amount of effort, the amount of force to get there. By increasing this distance, we decrease the force of doing that, so the effort. So let me show you what I mean. And to do that, we're going to talk about something called, in fact, let's hold off 1 second here. I want to do a quick question. Let me go ahead. Is there any questions on that before I go on? Any questions about this right here? If you agree with this statement, raise your hand. Are these steps in an inclined plane? Excellent. Just about everybody agreed that they are inclined planes. They very much are. Okay. And what is the shorter distance? Leave this as an answer to me. Going up a ladder that went straight up, or going up and down these ladders that go back and forth? Which of those is the quickest way? Give me some answers here, folks. Remember, we're talking about distance traveled. Excellent. We're getting a lot of good answers. It's the same amount of work in both cases, but it is a different amount of distance and a different amount of effort. All of you that are saying, which is almost everybody, faster going straight up is correct, but it'd be a lot more work. And give you a perfect example of why, if you've ever noticed, when we make buildings wheelchair accessible for people, as something we should certainly be doing, you notice they make the planes, the inclined planes, much longer, and that helps the people that are using a wheelchair or pushing a wheelchair to get up. It gives them by making the inclined plane longer, it makes it easier for them. So if you ever notice, when next time you walk by, notice that. All right. Now, there's two ideas here. I want you to know we're going to be calculating the theoretical or the best case, the IMA, the ideal mechanical advantage, versus actual mechanical advantage. And IMA is the theoretical output force divided by the theoretical input force. Don't worry, folks. We're going to get to this in a minute. So just chill if you see this. Where actual is the actual forces. If we put a device on it, we actually measure the forces. Because in reality, and this is why I just want to say, whenever you have a theory, you do a calculation, you always have to have some kind of factor in there to consider that nothing works as in theory like it does in real life. In terms of it's never as efficient in real life as it is in theory. And the reason is that is friction. If you think about it, once you start rolling a car down a hill, there's no reason you should ever stop. But that friction causes it to stop. If you've got levers or you've got gears, the axle of the gear will flex and move, and that causes it not to run quite perfectly. So we're going to calculate the IMA. In reality, it's probably a little bit less. It's the actual output AMA is going to be a little bit less. It certainly can't be any higher. All right. All right, 6 classes of simple machines. All right, this is where you got to take a little bit of notes, folks. But this will help you in school. This will help you if you do robotics. This will help you to understand all these things. Okay? All right. So let's do this. All right. So, in an inclined plane, the IMA is equal to length divided by height. Length divided by height. The length is the length of this wedge divided by the height. So you're walking up this distance right here. So here we got a series of questions. We're going to take our time. We're doing really well on time. An inclined plane that is 6 meters long and 3 meters high. What is the ideal mechanical advantage of this? Inclined plane that is 6 meters long and 3 meters high. What is the ideal mechanical advantage here, folks? So let's start listening and let's get everybody involved. Let me pull this up so I can see the questions. Excellent. All right. So if it's 6 meters long, right, it's 3 meters high. We said by definition then 6 divided by 3, the mechanical advantage is 2. Okay? Folks, please answer because I don't know if you're getting them right. When we go back and review the answers and things, we need to see this. A ramp inclined plane has an ideal mechanical advantage of 3. So we're going to start off this time. It has the mechanical advantage of 3. It's 3 meters high. How long is it? All right. So let's think about what is the formula for ideal mechanical advantage? Well, it's simply IMA equals the length divided by the height. Well, we don't know what the length is, but we do know the height. The height is 3. IMA is 3. If you do a formula, it's going to be 3 equals the length over 3. 3 times 3 equals L. or L, the length, equals 9 meters. Well done, folks. Excellent. Now I've got the same folks answering these questions, which is really great, but I need everybody else to be involved. The next question, I'm gonna go ahead. I'll be quiet for a few moments, and then we'll unmute you and we'll ask you out loud. All right. Again, just use the formula. Key thing when they give you a question on a test, there's got to be a way to solve it. And in the beginning, at least use the plug and chug, where you know the formula and you just figure out what part of the formula you don't have. So, in this case, we have a stairway has 8 meters long with an IMA of 2. So how high is it? Well, we now know we don't know what the height is, right? So we say, well, IMA equals, all right, IMA equals 2, so we say 2, IMA equals length over height, so that would be 2 equals, it's 8, so 2 equals 8 over h. Well, we're going to solve for h, height. 2h equals 8. What's the answer, folks? All right. Now I'll ask everybody here because we'll get everybody going. Just take your best guess, folks. There's nothing wrong with it. Ryan, what do you got?
4 meters high.
You got it. Well done. How many people figured that out? Raise your hand if you got it right. Nice. Nice. All right. Not everybody got it, so yeah, anybody have questions about it? That's what I'm here to do. You make me feel useful if you're here for me to answer questions. Okay, raise your hand if you have a question, because then I'll call on you and I'll try to answer it. All right. I've got one person still saying he's got a question. All right, so I'm going to ask him. Can you hear me? Shukla. Okay, I'm not sure he can hear me or I can't hear him, so we'll just... Oh, I got it. There he goes. Hey, hello?
Could you please repeat the answer for that question?
The answer for that question is 4, because the IMA is 2, right?
Okay.
2 equals, it's 8 meters long, and that's the top of the equation. 2 equals 8 over the height. Solve for h, and you end up with 4. Does that make sense now?
Yes.
All right, good.
Thank you.
You bet. Anybody else? I just put 1%. Anybody else got a question about this before we go on? Okay. Sorry for the yawn there. I've been teaching all day. All right. There's 6 classes of simple machine. We just did inclined plane. Now we're going to do a wedge. We're going to do a wedge. A wedge is really, if you think about it, is 2 inclined planes stuck together. And we use it to split trees, for example. All right. And there's an example of a wedge right here. Classic. It's this length divided by the separation. So it's the depth of the penetration right here, and then the separation, little t. So that's L over T. Will give you the IMA. All right. A wedge is 30 centimeters long and 3 centimeters wide at one end. What is the ideal mechanical advantage? Okay, let's look at the questions here. Good job, folks. You're that way to be participating. Well done. Here we go. Let me pull them up. Okay. Is that right? There we go. All right, so if the wedge is 30 centimeters long and it's 3 centimeters wide, and the AMA is equal to length to the width divided, or how do you put it? Let me say it a little bit better here. It's the depth of the penetration, we just said that was 30 centimeters, by the separation, 3. So 30 over 3 is 30 centimeters over 3 centimeters gives you a mechanical advantage of 10. Well done, folks, that are doing this. Well done. Should I choose a long wedge with a narrow end or a short wedge with a wide end for the best IMA? Tell me which wedge I want. No, you were right to begin with. Jaden, you were right to begin with. It's 10 there, buddy. IMA of 10. All right. If you would, folks. Already got one answer and it's correct. Yes. Keep it up, guys. Think about it. Which one? You got a choice there. A, the one with a narrow, long wedge with a narrow end, A, or a short wedge with a wide end for the best IMA. Great. Excellent, excellent. Everybody's saying the long edge wedge with the narrow end. Y'all are just knocking it down. Good job, folks. Well done. Can't wait to tell Mr. Maurer about it. 6 classes of simple machines. We've done incline, plane, and wedge. Now we're going to do a screw. I'm going to describe it to you. We're really not going to do the calculations on it. You can see here's a screw jack. We can use that. It's a case of the length of this right around here divided by the distance of these threads times pi. We're not going to worry about that here. Okay, but that is a screw. And really all I really want you to know is if you take a screw as an inclined plane wrapped around a nail, basically what a screw is. It's one of the last simple machines invented, by the way. All right, now a lever. Our friend Archimedes said, give me a lever and I can lift the world. You give me a long enough lever, I can pick up the world. All right? And he designed some really neat things with that fact. So here's our first class lever. There's 3 classes of levers. First class, second class, third class. First class, then is the fulcrum's in the middle. There's an output and input in the fulcrum. In the second class, the fulcrum's moved over to the side, and the output's in the center. That's like this wood here when you're picking up a wheelbarrow. This is why you always want to grab the far end of the wheelbarrow. This gives you more leverage on this. So again, just think what's in the middle. In a first class lever, what's in the middle, folks? Go ahead and write down an answer. In the first class lever, what's in the middle? In a first class lever, it's the fulcrum. See right here, that's in the middle. In a second class lever, it's the output or the load. Your input right over there. And then in a third class lever, before we even do it, we saw in the first class it was the fulcrum. Second class it was the output. What do you think's in the middle of a third class lever? What do you think's in the middle of a third class lever? So far, I'm getting lots of right answers. Well done, folks. Everybody's already answered. You've gotten it right. What is in the middle of a third class lever? All right, what's in the middle of that third class lever is an input. Think your tweezers. You grab your eyelash right at this end, right? And there's the fulcrum on this end, the part that balances, right? And where do you put all your effort? Well, you put it right there in the middle. That is a third class lever. Salad tongs are a third class lever. I'm going to see what's going on here. We losing folks? All right, no, we got the same number. All right. All right. So, what are these class levers? You've got one here, here, and here. I'll tell you where the fulcrum is, and you tell me what it is. Believe it or not, the fulcrum on this one's on this end. Effort is on this end. So fulcrum's here, effort's there, the load is in the middle. What class lever is that one? First, second, or third? Pair of tweezers. Let me again say, effort's on this little tip here, fulcrum's on the other end. The load is in the middle. Okay, we're getting a whole range of answers here to now. Let's go back up and look at this one more time. Well, that's fine, guys. I'm going through the whole thing of simple machines pretty quickly here, so you're doing great. Fulcrum's in the middle. It's a first class. Output or your load is in the middle. It's a second class. Effort in the middle, input or effort in the middle, third class. I'm telling you, the output or load is in the middle of this one. Which one is it? Folks, the output or load is in the middle. It's in between our effort and the fulcrum. And that, my friends, is a second class lever. In this nail puller, we have the load is on one end, the nail we're pulling on. We put our effort in the handle. The fulcrum is in the middle. What is this? Now, what class lever is this? Remember, we're pulling out nails. This is our load is on this end. Our effort is on this end with the handle. Our fulcrum's in the middle. What one is that? Excellent, 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 excellent. Everybody's saying first class, and if you are too, then you're getting it right. All right? So, well done on that. On this one, we have a fishing rod. Okay? And on our fishing rod, we put the rod on our hip. Okay? And our load is at this end of it. So all our effort is in the middle. The effort is in the middle of the fishing rod. What kind of class lever is that? All right, all those people saying third class have got it right. Again, effort, input or effort in the middle, like a set of tweezers, third class. The load, what we're trying to carry, the output, in other words, in the middle, second class. Fulcrum in the middle, like a pair of pliers, teeter-totter, first class. All right. Now, time to get out that sheet of paper and do a little more calculations again. All right. So, we have an ideal mechanical advantage here for a lever. And what we're doing is we're basically saying, here's the fulcrum on this lever, right? We're saying length R divided by length E. So our effort arm, if this is really long, and the result, right, or that load arm that goes from here to the fulcrum is really small, we get a huge IMA. And that may not be obvious, so let me get you to think about this. Say, for example, you're out there and you're babysitting, and you got a little munchkin sitting on the other side of a teeter-totter from you. And she just weighs a little bit, but she's big enough to sit on the teeter-totter. She could sit on this side or this side. You'll put her here where she's farther away from the fulcrum, and you'll set up close to the fulcrum. You'll balance. Try that next time. All right? Also, this is why move your hands back on the wheelbarrow when you go to lift it. Whenever you get a lever, the farther away from the fulcrum on a first class lever, the more mechanical advantage you're going to have. All right. Here we go with these questions. But this will help you in class. You will cover this. If you don't cover it in middle school, you'll get it in general science in high school. So it's a kind of an introduction here. I'm pressing down on a lever. The distance from the fulcrum where I'm pushing is 4 meters. The load on the other side is 1 meter away from the fulcrum. So draw a little drawing right now on a sheet of paper, please. Draw the little triangles of fulcrum. Label one side 4 meters, the other side 1 meter. Push an arrow where you're pushing down on the 4 meter side. You draw it to scale, it's even better. In other words, draw one that's 4 times longer than the other. And say that's the one you're pushing down with. All right. So I'm pressing down on a lever. The distance from the fulcrum where I'm pushing is 4 meters. The load on the other side that I'm trying to lift up. So I'm trying to lift up stones. I'm trying to lift up my motorcycle that's fallen on the side. What is the ideal mechanical advantage? Guys, what did you come up with the ideal mechanical advantage? Most excellent. Well done. People are saying 4. Excellent. I've set up a lever so it has an IMA of 5. I'm using 2 newtons of force. How much load can I lift? I've got an IMA of 5. I'm using 2 newtons of force, so how much load can I lift? All right, so let's figure out our formula. IMA equals, right, the distance from the fulcrum of that I'm trying to lift, right? And then divided by, in this case, it's IMA equals, excuse me, let me restate this. equals the load I'm lifting, right, divided by 2. And so in this case, I can lift 10. All right? Excellent. All right, very good. We got people have 10. I'm using 2 newtons of force, newtons. I've got an IMA of 5, 2 times 5, I get 10. Okay? All right. I'm balancing a 20 Newton object. My lever has an IMA of 4. How much effort do I need? So I've got my lever that I've built has an IMA of 4. I've got to hold something that's 20 newtons. Well, how much effort do I need? All right, I've got, well, so let's think about that. IMA of 4, right? And I'm holding a 20 Newton object divided by my effort. So if I take my effort times IMA of 4, so let's say that's E, 4 times E equals 20. E equals 20 divided by 4 or 5. The answer is 5. Okay? The answer is 5 on that. Now we have a wheel and axle. This will be the last one we do. We'll have one more. We'll do, a pulley when we start off Wednesday. All right? My understanding is you've got Lab Tuesday. You do not have Lab Wednesday. So we'll do that. And I'd rather take our time to do it right. So far, before we go on and do wheel axle, any questions? Write down what your questions are. I really appreciate everybody who's answering. You're going to get a lot more out of this if you answer the questions. All right. And a wheel and axle. You know, it's a classic. We use them everywhere. But the the advantage of IMA of this is radius of the wheel, all right, divided by the radius of the axle. That's your mechanical advantage. The radius of the wheel, radius, go around this. This is diameter. This is radius. And then radius of the axle. The axle of my cart has 6 centimeters. The wheel has a radius of 60 centimeters. What is the mechanical advantage of this system? Whoops. Nice. You guys are crunching it. I'm telling you. I'm not sure where you came up with that. You're not multiplying it. You're looking at the formula. Please write out the formula on a piece of paper. We said AMA is, let's look at what the formula is. The radius of the wheel divided by the radius of the axle. Okay? Sorry. So, I said the radius of the wheel was 60. The radius axle was 6. That gives us an IMA of 10. Well done, folks. Oh no, the power steering has gone out in my Camaro. That's a car for somebody who wouldn't know. The steering wheel is hard to turn. I want the wheel to be easier to turn. Should I buy a steering? I want the wheel to be easier to turn. Period. Should I buy a larger steering wheel or a smaller steering wheel? Why? Do I want a larger one or a smaller one, guys? Of the wheel. Let's look at our formula again. This is how I'd approach this. Radius of the wheel divided by the radius of the axle. Do I want a small? I want the largest IMA because that'll make it easier to turn. What do I want? Not larger, so there's more. Large because of the formula. The radius of the wheel, the larger radius of the wheel. If that number's bigger, this number stays the same. IMA will be bigger. So if I keep increasing the size of this number, the IMA, and I don't change the axle, the IMA will get bigger. All right, all you got larger. Well done. Next question. I can't make the wheel any bigger. Do I increase or decrease the diameter of the axle to increase IMA? Look at that formula. Do I increase or decrease the diameter of the axle to decrease the the ideal mechanical advantage? Do I make the axle bigger or smaller? Let's look at our formula one more time. Do I want the radius of that axle to be bigger or smaller? Excellent. Most people got this right. You want to make this number smaller here. Say if the number was 8 and 4, and I can't change 8. 8 and 4, the IMA is 2. 8 and 2, the IMA is 4. 8 over 1, IMA is 8. So if I keep making that diameter of this axle smaller and smaller, it's going to get bigger and bigger. Folks, pat yourselves on the back. Most of you did very well tonight. Tuesday you got a lab. You're going to really enjoy building that. You'll be playing with mechanical advantages as you make your siege machines. And I look forward to seeing you Wednesday. Any questions? I will post this a little bit later tonight, probably early tomorrow morning. But I've been recording this webinar and we'll put it up for Iowa. Okay? Are there any questions? Okay. If there are no questions, have a good evening, folks. Okay? Bye-bye.